In this video, I'm going to introduce a topic called linear algebra. Linear algebra provides a set of mathematical tools that make it easier to work with linear systems of equations. Engineers spend a lot of time analyzing and designing linear systems, so the mathematics associated with these types of systems is important to us. In this video, I'll talk about some of the basic rules of linear algebra. We'll see how to add, subtract, multiply, and transpose matrices and vectors. Some linear algebra rules are similar to rules we've used when dealing with arrays. However, there are some important differences between the array operations we've been using and the matrix operations I'll be talking about in this chapter. So, when using arrays, you'll need to keep in mind how the array is being used so that you can know whether to use the array operations or the matrix operations on the numbers. Linear algebra operates on matrices, vectors, and scalars. Matrices are two-dimensional arrays, which are just tables of numbers. The values in a matrix are organized in rows and columns. Elements in an array are specified by two subscripts, which give the row and the column location of the element. For example, A22 is the element in the second row and the second column of the matrix A. Vectors are one-dimensional arrays with a single row or column, so they're really just a list of numbers. Elements of a vector are usually specified by a single subscript, which provides the location of the element in the list. Vectors can have either a single column, like X, or a single row, like Y. Scalars are single numbers. To differentiate between matrices, vectors, and arrays in mathematical expressions, I'll use the following nomenclature. Matrices will be specified by uppercase letters. Vectors will be specified by a lowercase letter with an underscore. Scalars will just be represented by a lowercase letter with no underscore. This notation will be important because the operations being done and the properties of the matrices can depend on their sizes. Officially, matrices and vectors are special cases of arrays. However, some terminology is used differently when referring to arrays than when it's applied to matrices. An example of this is the term dimension. Dimension means something different depending on whether we're referring to a matrix or to an array. For an array, the dimension tells us how many subscripts are necessary to specify the address of a particular element. A one-dimensional array requires a single subscript, which gives the position of an element in the list. Two-dimensional array elements require two subscripts to describe their location, the row and the column number. Higher dimensional arrays follow the same pattern. However, a matrix dimension tells you something about the properties of the system being described. Matrices and vectors are generally referred to in terms of the space that they're describing. For example, a three-element vector can be used to specify the x, y, and z coordinates of a point in three-dimensional space. First, I'll talk about addition and subtraction under the rules of linear algebra. These operations are the same as the array operations of addition and subtraction. The operations are done element by element. So, if a matrix C is equal to a matrix A plus a matrix B, each element in C, so C sub jk, the element at the jth row and the kth column, is the sum of the element in A at the jth row and kth column plus the element in B at that location. As an example, if I add these two arrays, I get this result. 1 plus 5 is 6, 4 plus 8 is 12, and so on. Multiplication of a matrix by a scalar is also the same as the corresponding array operation. If C is the product of a scalar A times a matrix B, the elements of C, C sub jk, are just the corresponding elements in B, each of which is multiplied by the scalar A. For example, if I multiply this matrix by 4, the result is this. 4 times 1 goes in this location, 4 times 3 is 12, and so on. Transposing an array simply changes the array subscripts so that the rows and columns of the array are exchanged. The symbol for transpose is a superscript T. So if B is the transpose of A, the subscripts of the B matrix are reversed. Rows become columns and columns become rows. So if I transpose this array, the first column 1, 3 will become the first row. The second column will become the second row. Next, I'm going to talk about matrix multiplication, and things are going to start to become interesting. Multiplying two matrices relies on what is called an inner product. An inner product is defined as a row vector multiplied by a column vector. If I multiply a row vector times a column vector, I get a scalar, C. To get C, I take the product of the corresponding elements in A and B and then add up all of those terms. For example, I want to multiply this row vector times this column vector. The result is 1 times 4 plus 2 times 5 plus 3 times 6, which is equal to 32. Notice that in order to do the inner product, the vectors have to have the same number of terms. I need a corresponding element in the vector B for every element in the vector A. Now I'll move on to multiplication of two matrices. In this operation, each element of the resulting matrix is the result of an inner product. So if C is the product of the matrices A and B, the element at the jth row and kth column in C is the inner product between the jth row of the matrix A and the kth column of the matrix B. Graphically, the process looks something like this. To get the element, which is a scalar, at the jth row and the kth column of C, I multiply the corresponding terms in the jth row of A and the kth column of B, and then add them up. Notice that the row vector of A and the column vector of B have to have the same number of elements to perform the inner product. This implies that the number of columns of the first operand matrix has to be the same as the number of rows of the second operand matrix. Let's try a simple example. I want to multiply this matrix times this one. The element in the first row and the first column of the result is going to be 1 times 5 plus 2 times 7. The element in the second column first row is going to be the first row times the second column, which is 1 times 6 plus 2 times 8. So after I add these all up, I get 19, 22, 43, and 50. Finally, I want to make a couple of comments about matrix multiplication. Matrix multiplication is not commutative, so that A times B is not the same as B times A. In fact, switching the order of the operands may not even result in a legal operation. Recall that the number of columns in the first operand has to be the same as the number of rows in the second operand. This condition is often summarized as a requirement that the inner array dimensions must match. So if A is an array with I rows and j columns, and B has m rows and n columns, I need j to be equal to m in order to multiply them together. Notice that here, at least, I'm using dimension differently than I've been using it for arrays. I'm now using it as a number of elements in a particular direction in the matrix, which is consistent with matrix notation rather than array notation. This concludes the first video on linear algebra. I've covered linear algebra rules for addition, multiplication by a scalar, transposes, and matrix multiplication. In the next video, I'll talk about using MATLAB to perform these operations and do some demonstrations.